I really like it.
No.
Do you bike from car?
All right, it's 4:09, but I believe it will be 4:10 by the time I finish this introduction. So I'll go ahead and get started. So my name is Amy Pavel. I'm a new assistant professor here in the computer science department, and I'm thrilled to get the rare opportunity to introduce my advisor, my PhD advisor, Maneesh Agrawala. Maneesh used to be a faculty member here with us at Berkeley until he left us for Stanford, where he is now the Forrest Baskett Professor of Computer Science and also the director of the Brown Institute of Media Innovation. Maneesh's work spans fields from graphics to human-computer interaction to visualization. And one thing I really liked about Maneesh's work over all these years is that his work is extraordinarily creative and thoughtful. And this isn't a unique opinion, so he's won a long list of awards, including a MacArthur Genius Award, and he was recently named as an ACM Fellow. And beyond the academic awards, he also has companies and practitioners who have picked up a number of his techniques. So recently, ControlNet, which is one of his recent works, has become this standard tool that exists in image generation software that's being used by a new wave of artists who use AI for creativity. So I'm super excited to hear what Maneesh has to tell us today about how humans and AI might collaborate more effectively in the future. So let's take give Maneesh a warm welcome back to Berkeley.
Thank you. All right. Well, thank you, Amy. It is awesome to be back here in this room. About 20 years ago, I gave a talk in this room that led to my becoming a professor here, so it's kind of a homecoming for me. It's also a bit nerve-wracking. But no, it's really great to be back here. And thank you for inviting me. We, in my group at Stanford, have been thinking a lot about AI and generative AI and how we can make better and more effective use of generative AI tools. And that's what I want to talk about today, but I want to start here with a question for all of you, if this works. Let's see. Okay, this will work. Okay, so the question for you is, who made this photograph?
Ansel Adams.
You are almost right. Okay, so while you think about Jitendra's answer, I just want you to take a moment to admire this photograph. It has a very careful use of tone and contrast. The photograph covers the full range of gray values, from deep dark black shadows through a gradient of gray in the sky, lighter gray in the moon, and then full bright white in the lit snowy areas. And this image is really quite majestic, and it's rightly, I think, very, very famous, all right? And as Jitendra said, this photograph is credited to Ansel Adams. But Ansel Adams wasn't the only person involved in making this photograph, okay? So Adams, on the left here, did indeed shoot the photograph, But this version of the photograph, the special edition, was printed on paper by his assistant, Alan Ross, who's shown over here. And Ross has said that although Ansell's hands were not in direct contact with the printing, his vision always was. The challenge was to be able to anticipate and respond technically to his requests. Make it a little darker over here. Can you make it a bit more contrasty, he would ask. So in his 6 years as assistant, Ross learned what Adams meant by concepts like contrasty. He learned to interpret what Adams wanted. And this photograph is, of course, credited to Ansel Adams alone because Adams is the person who had the vision, who made all of the critical choices about the overall look and the tone of this photograph. Ross assisted Adams in executing those choices. So here's another Ansel Adams photograph printed by Alan Ross. And again, look at the control over the tones. But here, unlike the last image, the sky and the tree are really use a limited set of grays and whites. And black is reserved for the tree trunk to make it really stand out. We can all imagine a conversation between Adams and Ross as they were making this image. So Adams might start by saying, "Can you make it a bit more contrasty?" Ross responds, "By contrasty, do you mean I should use the full tonal range?" Ross is checking that both of them understand the concept of contrasty in the same way. He's trying to ground the concept. Adams says, "No, let's use a limited set of tonal zones, 6 to 9 for the leaves and sky, and zone 0 for the trunk." Adams is invoking his well-known zone system of tonal zones. He assumes that both of them understand what the numbers mean. And this is a very well-known zone system. And he's assuming that both of them know it. This is a visualization of the zone system that comes from Wikipedia. So this, in fact, is known by many, many people. But at the time, we can imagine that they might talk about the tonal control with these zones. And what Adams is doing here is he's using conversational repair to communicate what he means by contrasty so that Ross can print this photograph to match Adams' vision. So their prior experience working together and the conversation allow them to establish a shared set of concepts that facilitate the creation of this photograph that Adams really wanted to make. And authoring content that you care about in any domain requires having opinions and making choices. Working with an assistant requires communicating those choices precisely to that assistant. So what does this all have to do with AI? Well, the promise of generative AI is that it can serve as a kind of collaborative assistant in creating content. An assistant that, like Ross was to Adams, that will help authors very quickly generate high-quality results, maybe in as little as 20 seconds, as suggested in this AI-generated magazine cover. Incidentally, I believe this is the first magazine cover image that was generated by AI. Okay, so let's work with generative AI to make an image. And what I really want to do here is to produce an image of Stanford's main quad, framed through the arches, with Memorial Church in the background, something like this real photograph, but I want it rendered after a heavy snowstorm. And AI is good for imagining something like this because snowstorms rarely happen at Stanford, right? So we need a tool that can make this for us. More specifically, I want to see if I can work with AI to make the tonal choices similar to the ones that Adams used in this oak tree image, with the sky and the church facade in white and light gray, and the arched entryways in full black. Now, I want to point out here that this is just an example of something that I want to make. I realize that not everyone in this room might be interested in creating this kind of image, but the process that I'm about to show you applies in many situations, really in any situation where you're trying to author something that you really care about and you're using AI as an assistant. So I start by giving ChatGPT 5 this prompt, and the result is actually, frankly, it's stunning. From the text prompt alone, I get a picture of the Stanford Quad with Memorial Church in the background, framed through the arches, and a significant amount of snow. The AI seems to understand the concepts of Stanford Quad, of Memorial Church, of framed in arches, and of snowstorm. But the one concept that I really care about is contrast. And here, the facade, I would argue, is dark gray. The mosaic detail is quite muddy on it. The foreground arch has very little contrast within it. And it doesn't at all look like that white and light gray oak tree image. So I ask for more contrast, and a few iterations later, I get this. And unfortunately, ChatGPT gives me a nighttime image that isn't at all what I want. So I try various words that might bring it back to the daytime. Here's iteration 7, and somehow ChatGPT forgets that I want a black and white image, even though it's right there in the prompt. And it gives me a bit of blue color in the sky, but at least it's daytime. And I get some contrast in the foreground arch, which I really like. So I now try to start to adjust the tones for that white on gray look of the oak tree, first using Adam's zone system with various wordings. At iteration 9, I get this, another nighttime image, unfortunately. It seems like ChatGPT might not know about the zone system, but I stick to it for a few more iterations, hoping that if I continue to use Adam's language, it might understand the concepts. Here's what I get at iteration 12, and we're back to daytime, but the tones in the sky and the facade are still quite wrong. And at this point, it's become fairly clear to me that ChatGPT doesn't know about the Ansel-Adams zone system, so I switch strategies and try to directly specify the tones that I want. And I try lots and lots of different wordings, and after many, many iterations, I end on iteration 27 with this. The image still isn't what I wanted, and I've basically given up. The facade is still too dark. The sky and the rooftop snow blend together to form a single continuous region. It's very hard to see the edges between them. It's partway there, but it's not really what I wanted to make. And what's worse is that I don't know how to adjust the prompt to communicate to ChatGPT how I want the image to look. I can't communicate my design choices very effectively. I wouldn't be comfortable with this result as representative of my work. To me, this end result is really an example of AI slop. And moreover, it took me several hours of essentially trial and error prompting to get to this point. So the question here is, how do we end up with this type of slop when we're working with human-AI collaboration in comparison to human-human collaboration, right? Why do we end up with this type of slop? Well, I think there's one key difference in these two types of collaboration. In human-human collaboration, we can establish shared conceptual grounding, as we saw with Adams and Ross, allowing the author to communicate design choices to the assistant fairly precisely. And we can do this based on prior shared experiences, on conversational interactions to facilitate the grounding, and the use of repair to fix ambiguities and misunderstandings. In contrast, with human-AI collaboration, there's often a lack of shared conceptual grounding. We have little shared prior experience. We have short conversational interactions. And we have fewer mechanisms for repair. Very, very few mechanisms for repair. And so the end result doesn't really match the author's vision. We end up with lots and lots of trial and error prompting, and we end up with slop. So while the promise of generative AI is that it will serve as a kind of collaborative assistant, the reality is that while they at first seem really amazing, the results can be stunning. They are terrible collaborators because we do not share conceptual grounding with them. And as we've seen, this is true for image generation. Even though this magazine cover claims that it took 20 seconds to make, the artist Karen Chang, who worked to make this cover, has published a TikTok video describing how it took her hours and hours of prompting to find the right one to produce this cover. She had, yeah, question?
Are you taking questions in the middle, or?
Yeah, if you'd like to, I'm happy to, yeah.
So, your conversation with ChatGPT,
Yeah.
it was to sort of get to some end result and get to some mutual understanding of what you want. But, one powerful tool is to provide examples.
Yeah.
Why don't you give the example of Ansel Adams' tree in falling snow and say, I want something like this?
Yeah, so examples can be helpful. And when I tried it with that, I tried to do what you said and gave it the examples. It didn't give me anything that was better. It didn't give me what I wanted, okay? And unfortunately, I don't have that at the moment to show you, but this happens all the time. Even when you give it examples, it doesn't always give you what you wanted because you haven't told it how to interpret the example, right? Do I want the snow from this example? Do I want the contrast? Do I want the content? Do I want a tree, right? What do I want from the example? You have to explain all of that. And the problem is the same problem. There's a lack of shared grounding. There's a lack of communication about what I want in a way that the machine, the LLM, understands. Okay? So she had trouble, here again, precisely communicating what she wanted to the LLM. And we've all probably experienced similar problems in working with AI because it occurs in every domain. So it shows up when I try to use an LLM to write text. Here, I have to ask for multiple rewrites of a one-sentence bio for myself, and I never got something that I really liked. It shows up when trying to use AI to make diagrams. Here I wanted a labeled diagram of a bike, and no matter how I prompt it, it mislabels the parts and includes labels that I don't really want, right? It shows up when using AI to generate video. So in this case, I wanted a close-up panning shot of an elderly man in a beret sitting in a cafe, and it produces, well, this fairly inconsistent mess, okay? So it shows up whenever we're using AI these days to make anything, to make music, to make animations, to make 3D objects, really to make anything. So what we've seen so far is that authoring content in any domain is about being opinionated, about making design choices. And working with an assistant requires communicating those choices precisely to the assistant by building a shared set of concepts. Shared grounding lets an author predict how an input request to the assistant will affect the output, right? And lack of shared grounding forces authors to resort to kind of trial and error prompting, trial and error requests, and often leads to slop. In fact, recent articles in the Harvard Business Review and the New York Times have started to recognize the problems with AI-generated slop and AI-generated content. Too often, the content seems like it's well-suited to the task at first, but is problematic on closer inspection. And these articles explain how such slop is starting to lead to disillusionment about the place and value of generative AI tools in general. So I think that for AI tools to have value, those of us working to build them really have to provide interfaces that let users build shared conceptual grounding with the AI. But of course, this is very challenging because no one has a really great understanding of what these AI tools are doing under the hood. So the question here is, what can we do? Well, we can start to think about the properties of effective AI tools and how they relate to shared grounding. So inspired by some work from HCI, I think there are three key properties that can support shared grounding with human users. First is consistency. We should teach AI shared structures that should be maintained across AI operations. We want to teach the AI about locally independent concepts. So here in this drawing example, the tool is, in this case, a pencil, and each stroke changes a little bit of the drawing, but it doesn't change the entire drawing. There's a kind of consistency from stroke to stroke, and each stroke is sort of an independent concept. They start to work together, but they're locally independent from each other. And I think that's important. We need to teach the AI about concepts that are dependent and independent. We also need to have support for hierarchical decomposition. We want to teach the AI about levels of abstraction. We want to teach the AI how to break down high-level abstractions and concepts into sequences of simpler concepts, lower-level concepts. We want to break complex workflows into sequences of simpler AI operations. So here, the artist starts by drawing the overall shape of the major parts of the body, designing the composition and the layout, the pose of this character, and then adds in the detail strokes, right? And so we want to support this kind of decomposition. And finally, the third property is rapid do and undo. We've known for a really long time in interface design that speed and undo is critical for our tools. And so we've put a lot of effort into improving execution speed and also implementing things like undo stacks. In the context of AI, we want to teach the model to learn from its mistakes, right? And we can think about this as a place where we can start to use concepts from reinforcement learning and verification to let the AI learn from the kinds of problems that it might create during the creation process. So we want to support this kind of do and undo, and there's many ways we can do that, but in particular, I'm interested in how we can use this to help teach the AI to learn from its mistakes. So I'm going to focus this talk on the first two, and if there's time at the end, I'm happy to take questions about the third as well. Okay, so let's talk about consistency, and I want to start with an example. In her classic book, Drawing on the Right Side of the Brain, Betty Edwards has explained how artists often start a drawing by sketching its spatial composition, something like this, okay? But in 2023, 2 years ago, text-to-image generators, diffusion models were the big ones at the time, forced users to specify layout and composition using a natural language prompt, like this one. And this prompt is really imprecise about the spatial composition. So here, the layout of the windows, which is easy to draw, is hard to specify in the text. And when I feed this to a text-to-image generator, I get a building facade like this from the prompt. It doesn't match the composition that I wanted. Moreover, each adjustment to the prompt produced a completely different image. Now, this was back in 2023. A lot of these problems of this kind of consistency have been improved, and we saw that in the Stanford quad example earlier. But at the time, every new change to the prompt completely changed the image, and that wasn't so good. So my student Lumin Zhang worked on ControlNet. And the idea here was that we want to give the text-to-image generator not just a text prompt, but also a control image. Here, a kind of drawing, a sketch of the facade, or maybe a pose of a human person, and then feed it to the ControlNet text-to-image generator and produce images like this, okay? And all of these images match the spatial composition provided by the input control image on the left, right? And by changing the text prompt, you can specify whether the facade should be a view from the outside of the building or the inside of the building. You can specify that the person that it generates should be a chef. And we can get two very different looks of the chefs, but all of the poses of these people match the control image. And this has subsequently been taken up by lots and lots of image generators. It's a core tool that lots and lots of AI artists are using today because it provides this kind of spatial control that also agrees with the ways that artists often think about making images, right? Starting with spatial composition and then adding in details. Okay, just a little bit briefly about how ControlNet works. It's built on top of Stable Diffusion. Stable Diffusion is a diffusion-based image generator. A noisy input X goes into a neural network block. If you're familiar with these kinds of diffusion models, you can think of this neural network block as a U-net. It's the base backbone of Stable Diffusion. That U-net is denoising the input image X, and we get a denoised image Y at the end. With ControlNet, we add in this part on the right. We keep the neural network block, the U-net, locked, and we add in this trainable copy on the right, and we add in the support for a conditioning image, the edge image or the pose image coming in here at the top. It's passed into the trainable copy of that backbone, the weights in the U-net. Through this zero convolution, we pass it all the way through on the encoding layers, and then back through a zero convolution layer, and then passed back to the denoised image. So the key thing in this design is that we are keeping the original backbone of Stable Diffusion locked, but we're adding in this trainable copy, and we're doing it through these zero convolution layers that are initialized with weights and biases of 0, and this allows the zero convolution layers to progressively grow in size and progressively train up the trainable copy of the backbone. And this is designed in a way to significantly reduce the problems of catastrophic forgetting that you often get if you directly try to fine-tune the original neural network U-net. Okay, so this zero convolution layer was especially important to the efficiency of the system, and what we found is that with as few as about 500,000 training examples of edge images plus the corresponding real image, we could fine-tune Stable Diffusion to produce fairly high-quality results. And we could do this in as little as 600 GPU hours. And that's in comparison to training Stable Diffusion from scratch, which was trained on billions of images and took about 150,000 GPU hours. So a big part of the control net story is that we could train it and fine-tune it very, very efficiently. And the recipe went out with our model so that others could train their own control nets fairly efficiently. Okay, more recently, Lumen, who worked on ControlNet, has developed tools for generating foreground and background images together in a consistent way with this layer diffuse project. The idea here is that you give it a text prompt. These text prompts are at the top, and it generates an image, the image below, but this is actually a layered image. So we have a background layer, that's a full, complete image, and a foreground image that you alpha composite with the background to get the image on the top. And lots and lots of artists work with layered sets of images to compose their imagery. And so this is a pipeline that fits well with the kinds of tools that artists are familiar with. If you work with an artist that's using Photoshop, they will often set up layers like this to make their final imagery. The key idea of this layer diffusion approach is to train an encoder for the foreground alpha channel into latent offset vectors that work in the latent space of Stable Diffusion. And critically, we can add these latent offsets to a latent representation of the original RGB image, the original RGB foreground, and then decode that RGB part of the image using Stable Diffusion's decoder, frozen as is, even though we've added these latent offsets. We can also train up our own decoder that can decode that latent representation back into the RGB image and the alpha channel. So in a way, what we're doing here is we're hiding the alpha channel information in the latent space of Stable Diffusion. And it's a high enough dimensional space that we can do this fairly effectively, okay? And I think this is a pretty neat idea, and one that can go beyond just hiding this information about alpha channels. We can hide other kinds of information about these images in this latent space, and then use that for various applications. But in our case, we mostly focused on these alpha channels. And once we've trained a model like this, we can do foreground conditioning. So here we give the foreground image and a text prompt, and it generates backgrounds that are consistent with that foreground. So here it generates a background where a person can be sitting on this ledge, a church background that looks appropriate for this foreground bulb, and by changing the seed to the generator, we can generate different backgrounds that are, again, consistent with the foreground. We can do the similar thing with background conditioning. So we provide a background and a text prompt, and we can get a dog that looks like it's sitting on that sofa, or a woman sitting on this bench. And just by a change to the text prompt, we can get the cat or the elderly man. Last year, we also started looking at the problem of relighting images. So here's an image where I like the person, the way the person looks, the pose of the person, but they're outside in this image. And I would really like to see what she would look like if she were inside a room being lit by sunlight streaming in through a window. And so with our IC light model, we can relight the image and produce something like this that's still very consistent. It looks roughly like the same person, but lit in this very different way. And so here's the interface. And what happens is that you start with an input image, like the one over on the left. And we use standard tools to extract the foreground person, in this case. And then we type in a text prompt that describes the background. And our IC light model generates the image on the left. it generates the person, the foreground person, lit as if they're in the generated background. And we can change the prompt and put her in very different lighting situations. Now, the key constraint in this IC light model is based on the physics of global illumination, and particularly the linearity of light transport. In the paper, what we show is that we can incorporate the constraints imposed by this linearity into a loss function in an image generation diffusion model. And one thing we found really exciting about this work is that we released the models online, and very quickly artist communities took this one up as well. Here, someone created this comfy UI setup, and they just made it so that you could move the light source around and you could produce this animation. Now, our model has no notion of frame-to-frame coherence, and yet it's able to produce a fairly consistent look on this foreground face. All right, so that's what I wanted to tell you about consistency. I want to end here by talking a little bit about hierarchical decomposition, breaking complex workflows into simpler sequences of AI operations. And I want to start by thinking about the current way in which we work with AI. Often we start with a prompt, feed it to an AI, and we get an output result. And if we like the result, great, we can use the result and move on. But often, as we've seen, the result doesn't quite match our needs. There's some parts of it that don't match our vision, that we don't like. Maybe there's some artifacts we'd like to change it. And today, the only way to change it is by throwing away the output and going back to the prompt and trying a new prompt. And that's what leads to this iterative trial and error. So there is an alternative approach that people are starting to explore. And in this approach, you start, again, by giving a prompt to the AI, but instead of generating the output directly, it outputs code, right? It synthesizes a program, and that program can then be executed to generate the output, right? And so you might ask, well, why should I generate this code, right? If what I want is the output, why do I need the code? Well, the code has lots of good properties, but one of them is that a human, an author, can go in and look at the code. If there's something they don't like about the output, maybe they can go in and debug the code, fix those artifacts, right? Or maybe they can provide feedback on the code and send it back to the AI and have the AI try again using that feedback. And what I think is particularly exciting about this is that the code can be written using any domain-specific language, right? We can decide what the code primitives and the code grammar are, and those can be relevant to the domain. In fact, the human author could provide the DSL, and that DSL provides a kind of shared grounding of the concepts that are relevant to the domain. And so this is another way that we might be able to teach the AI about doing this kind of hierarchical decomposition, or at least to work with it. So we've started to take some steps in this direction as well. And so our work, our domain in this case, is making motion graphics animations. These are kind of basic 2D animations. You often see these in web advertising and other places. And the input in this case is a static SVG. So this is the SVG code and the rendered representation. It's a static image. And a natural language prompt describing the animation that I would like to produce. Here, I would like to move the orange circle, the dot of the eye, to the top of the stem, the rectangle. I would like to rotate the H by 90 degrees clockwise, and I would like these two animations to happen at the same time. That's what's being described. And I can use in-context learning to ask the AI to generate an SVG motion program, which I then execute to produce this output. Okay? So this is a fairly standard approach. Lots and lots of people are using AI, LLMs, to synthesize code, right? And we're just doing the same thing. We're just asking it by prompting to generate this code. And again, the nice thing is that as a human, I can go in and fix the code. In this case, what we see is that the dot doesn't quite get to the top of the I. And I could go in and fix that by fixing the code. Or I could provide feedback. I could tell the system that the dot isn't translating as high as it should and feed that back to the AI. But in this work, what we did was we started to question whether the AI itself could provide a kind of verifier for this animation. And so what we do is we ask the AI to generate a verification program written using a DSL, a domain-specific language that we provide. The domain-specific language is a first-order predicate logic language. And we're starting to see an example of it. And what the AI is basically being tasked to do is to convert the natural language specification into this verification program, all right? So this first line is checking that there's an orange-colored object that's shaped like a circle. And here we're checking for a rectangular object. This is the stem of the eye, and that there's an H-shaped object. And then we start to check for the motions. So we're checking that there's a translational motion that moves the dot to the top of the stem. We're checking that there's a rotation of the H by 90 degrees clockwise. And we're checking that these two motions happen at the same time. All right? So we've asked the AI to translate the natural language specification into this, and we're using the same zero-shot in-context learning approach. Once we have that, we have our own execution engine that can take this program and execute it against the SVG motion program to produce a report that tells us the things that passed and the things that failed. And what we find is that this first motion, the translation of the dot, the orange dot, doesn't get all the way to the top of the rectangle. So these parts of the verification program are false. The rotation by 90 degrees is true. And these two motions don't happen at the same time. So that's false as well. And we can take that report and now feed it back directly to the AI and ask it to try again. And it can try again, and it produces this animation that's slightly better. In this case, we can see that it's correct. It matches the prompt. And in fact, if we check it again with the same verification program, we evaluate to true. And so this is an automated way that we can go from a prompt to a correct animation, right? We can automatically iterate again and again until we pass the verification checks. Okay, so a key part of this work was to design the underlying first-order predicate language for verifying animations that are specified in natural language. And so the predicates come from prior work in cognitive psychology from Barbara Tversky and Talmy, who have described experiments where they ask people to describe the motions that they see in an animation. And from that work, they suggest that people think of and describe animations in terms of a basic set of things, the objects that they're seeing on the screen and the basic motions that they're performing, the translations, rotations, scales, the direction in which things are moving, how far they're moving, and so on. So those are the basic predicates, and those are designed to match the kind of descriptions you might see in natural language. Another thing that people do is describe motions relative to one another. We might have one motion happening before or after another motion, or while another motion is happening. And here we're relying on Allen's interval algebra, which describes various kinds of timing relationships between two motions. We can also have spatially relative motions, and this is essentially the two-dimensional analog of the temporal, of the interval algebra to 2 dimensions, where we get this rectangle algebra and these 13 predicates of relative spatial positions. And so those are the basic predicates in our system. And just to show you some more results, here's a natural language specification where I want to turn the word wow into the word mom by rotating the W's and then moving the O down to form the word mom. And in the first iteration, it properly rotates the W's, but it doesn't move the O down to form the word mom. With the verification in the first iteration, we get some motion of the O further down, but still not all the way. And in the third iteration, we finally get the correct result. And we've tried this on other kinds of specifications. Here's a specification asking to form these different numbers. And this required 2 iterations. And then here's an animation that is trying to make something that resembles a human eye, kind of moving around. This took 5 iterations to match the specification. Okay, so we developed a test set of about 5,600 prompts, trying to see various ways of specifying motions in natural language. And we fed these to GPT-4o and asked it to produce those verification programs. And it did that with about 95% accuracy. So we felt pretty good about that. It seemed like it could generate those mover programs well. And we see that it did that fairly well across the different kinds of prompts. So single atomic motions, spatially relative, temporally relative. When we combine spatio and temporally relative prompts, it gets a little worse, but it's still pretty good overall. And the other thing we did was look at the effectiveness of the full synthesis and verification pipeline. So how much is correction helping? Without iteration and correction, the LLM, in this zero-shot way, is able to produce about 59% correct animations from the text prompt. And when we add in this kind of correction... Sorry, what was that?
Correct 58.8%. How do you measure correctness?
Yeah, it matches, it passes the verification test. Yeah, okay. So, and here, with the verification and iterations, we're able to get it up to about 93, 94%. Okay? And we allowed it to run for up to 50 iterations, but usually it got it correct by around iteration 8 or 9. Okay? And then the other thing that we see is that it does fairly well across the board, except for spatially relative prompts, right? That's where it has the most trouble. So there's still some more work to do here. Okay, so I've told you about a bunch of stuff today, but there are a couple of key takeaways, I think. So one is that content creation requires shared grounding between an author and an AI assistant. And a lot of the problems that we run into today, I believe, happen because of a lack of this shared conceptual grounding. To have AI tools as effective collaborators, we should really think about how we can provide consistency, hierarchical decomposition, and also rapid do and undo with this kind of verification loop. I think there are lots and lots of open opportunities here. We're just starting to think about how we can deeply connect lessons from human-human collaboration to human-AI collaboration. And I think a lot more work needs to be done here. But the open opportunities are around what kinds of structures should we maintain consistency around, right? How to break complex instructions into simpler ones, right? What are the right decompositions? And this is likely to be task dependent. And then how can we more effectively use verification and reinforcement learning to teach generative models to learn from their mistakes? All right, with that, I'd like to thank the people that made this work happen. The names in blue, those are the students and postdocs that really did the work, so keep your eyes out for them. They are fantastic. I'm happy to take questions, or feel free to contact us. I'd love to talk with you about any of this. Thank you all very, very much.
All right, thank you so much for the wonderful talk. We'll take about 5 minutes of questions here, and then Maneesh will be able to stay afterwards for a little bit longer for more questions. Go for it.
Okay. Wonderful talk, Maneesh. So I have a philosophical question here.
Yeah.
Okay. Which is to do with the use of language. So it's clear that there needs to be communication that needs to occur between the human and the AI. But language is a bottleneck. When we humans communicate, we do not just use language. I mean, we use gesture, for example. We draw examples on a board. Just language seems like a bottleneck, and sometimes it may be quite natural. I mean, see, when you're talking about debugging computer programs, since they are in language, the language to communicate the differences is language. But often when we are in the space of images or video, I mean, this is fundamentally a different modality, and to coerce it into language seems an act of violence.
Yep. I fully agree. So, I think that particularly for visual things, we need to consider other modalities of communication. Gesture is a huge one. Gesture is one that's underexplored in HCI, and we need to better understand how people communicate with one another through gesture. The cognitive psychologists have looked at this a bit, but I think a lot more work needs to go into this. My colleague Judy Fan at Stanford is also thinking about gestures in the space of drawings. And we make gestural drawings often to communicate to one another. When we're standing at a whiteboard, we make these gestural drawings to indicate various things that are very, very ephemeral and have meaning in the moment, but that meaning can also go away over time, or is really established right then between the pair of people that are talking, and then will be unintelligible to others. And so there are these kinds of issues that I think start to come into play.
Take one more question. I saw your hand second. There you go.
Thank you. Could you go back a slide? Thank you.
Yeah. This one?
Yeah, so like in the hierarchical decomposition part, we talked about how to improve the performance by doing iterations. I consider it to be kind of like reinforcement learning, but how does it like different with like in the first part, like we say, we give the prompts
Yeah.
to improve the performance, and we ask the computer to run itself to iterate and to improve the performance.
Yeah, they are related. I think that what is interesting here is to think about levels of abstraction. So concepts have different levels of abstraction in which you talk about them and work with them when you're talking to another person. Sometimes I talk about this table as a table, and sometimes I talk about it as a piece of furniture, right? And the level of abstraction is something that is important for the shared conceptual grounding. So, and that's true for the concepts as nouns, but also for the concepts as instructions. We need to be able to break down these concepts into lower level and higher level concepts depending on the task at hand. Does that make sense?
Excellent. I'll end the open question session here, but I believe we have a bit of a buffer. So if you would like to ask your questions, you can come up afterwards. Let's thank Maneesh one more time.
Thank you. Thank you all.